second video for Chapter 8. We're going to look closer at collisions and the two types of collision, and then we're going to talk about impulse. But before I do that, in the previous video, I said there were 4 quantities that are conserved in physics, and those are mass, energy, momentum, and charge. Sometimes momentum is actually broken apart into linear momentum and angular momentum, and in that case we can think of it as being 5 conservation laws. Right now we're looking at conservation of linear momentum, but charge was the one I couldn't remember, but of course we're studying charge next semester. Now, there are 2 types of collisions. We have collisions that are called elastic collisions. In elastic collisions, momentum and kinetic energy are conserved. In an elastic collision, normally to have what we call, you need 2 objects that are really hard, like marbles or pool balls or steel ball bearings, something like that. What happens is the 2 objects roll towards one another, they collide. At the moment they are colliding, the kinetic energy is briefly stored as potential, which is what happens. The atoms, even though they're very, very hard, those atoms compress just a tiny bit, storing it, and then they move back apart. And if you calculate the kinetic energy before the collision and the kinetic energy after the collision, you'll see no kinetic energy is lost. Now the reality is a perfectly elastic collision is a bit of an ideal. There's really no situation where there's probably not at least a little bit of heating when there's that collision. A tiny bit of energy lost. But if things are hard enough, it's minimal, and we think of that as an elastic collision. Okay. The other type of collision is called inelastic. In an inelastic collision, momentum is conserved, but kinetic energy is not. So when we have an inelastic collision, the kinetic energy after the collision is going to be less. That's because often in a collision, a large amount of energy is converted to heat. We lose it. Things are designed that way. I know people fuss about how in a small car accident, sometimes it seems like the whole hood of a car can crumple up. That's almost deliberate because it acts kind of like a shock absorber, and it converts a whole lot of that energy into heat and actually makes a safer collision and a slower stopping time for the people inside the vehicle. In an inelastic collision, let's suppose that we go back to this idea of marbles, although it's hard to do this with marbles. You have them rolling around. I'm going to let this one be at rest. But if I put a little piece of gum or sticky stuff, say gum there, When this collision occurs, they won't just bounce off each other. They stick together. And after the collision, you have something more like this. They go moving off together. Now, when you have a situation where both objects stick together and there's no loss of mass, that's a perfectly inelastic collision. Now, the reality is lots of collisions, if we want to go back to the idea of cars, they may stick together, but they may also have bits and pieces that go flying off in different directions. They're usually somewhere in between perfectly elastic and bouncing off each other and perfectly inelastic and sticking together. Okay. When we lose this kinetic energy here, it's because there's some thermal heating. Some of that kinetic energy gets converted. Right. We're going to look first at some examples of inelastic. So let's go back to this idea of having some gliders. They're on an air track, and they're going to stick together. So we'll do those same two gliders. And this is glider A, and it's 0.50 kilograms for A. And it's initially moving with a positive 2.0 meters per second. It's moving to the right. Glider B is smaller. And it's initially moving to the left. Now, if we just stop and think about this for a minute, it's obvious when we look at this, they're on this air track, so they're not going to get stuck. There's no friction. This one has more momentum. We can tell because it has more mass than this one does. So if we put some Velcro and they stick together after the collision, so if they stick together after the collision, there's actually only one final velocity because they have to be moving at the same velocity. So this actually makes for an easier problem. There's only one final velocity. So again, we think of the initial momentum before, the final momentum or the after. So we have mass times velocity plus mass times velocity. There's A and B before the collision, and then we have after. Well, after we don't have two things. Here's after. We have enough common sense to say they're going to be going to the right since A had more momentum than B. So, what's the total mass? Well, now when we say mass is the 0.5 plus the 0.3. And they'll be moving at this final velocity. So that was 1.0 minus 0.6. So this side was 0.4. This is 0.80 final. You can see it's going much slower. Both of them were going 2 meters per second before the collision as far as speed. Afterwards, the whole thing's only going 0.50 meters per second. One of the questions they like to ask is, how much energy was lost? Well, if we're going to figure out how much energy is lost, we need to figure out how much energy do we have at the beginning before the collision, how much energy do we have now after the collision. So I'm going to erase some of this work, but I am going to write V final down. V final for both was a positive 0.50 meters per second. So initial kinetic energy, 1/2, this is for A plus B, so here's A, and here's B. Notice the negative makes no difference because we're squaring it, so 1/2 mv squared plus 1/2 mv squared, and this comes out to be 1.6 joules. That's my initial kinetic energy. My final kinetic energy, now I have that combined mass of 0.8, but I only have a speed of 0.5 squared. It comes out to be 0.10 joules of energy. That was a lot. To find the energy lost is simply subtracting, depending on how I write it. If I do change in kinetic, that's final minus initial, 0.10 minus 1.6, negative 1.5 joules, or I can just say 1.5 joules lost. When you have an inelastic collision, you are going to lose kinetic energy. Let's do one more example that involves this type. Let's go back to that car and truck from the last video. I'm going to write everything down so we can see what we've figured out already. In that problem, we had the truck was going this way, east. That was 2,000 kilograms, going 10 meters per second. And the car, 1,000 kilograms, was going 15 meters per second. And after we added the momentum for those two cars, we found they had a combined momentum before they hit that was 25,000 kilogram meters per second. And it was at an angle of 36.9 degrees. Now, if you don't remember how we did this, go back and look at the video, the first part for chapter 8, because we already added those two momentum together. If it's a perfectly inelastic collision, what's going to happen is they're going to stick together, and they're going to go flying off this way, and they're going to make that angle of 36.9, and they're going to have a combined momentum of 25,000 kilogram meters per second. Momentum will be conserved. Okay, the momentum before has to equal the momentum final. So the second part basically is just what's the speed and direction of the wreckage after they collide and they stick together. So this is a perfectly inelastic collision. If they collide and stick together, we know that the final momentum has to equal the initial. Well, this is the initial. Has to equal mass times velocity. The mass is the combined mass. 2,000 plus 1,000 V final. So that's 3,000. I just have to do 25,000 divided by 3,000. And I get that the final velocity is about 8.3 meters per second at an angle of 36.9 degrees. Momentum before, momentum after. The after is when they stuck together. Now, similarly, we can calculate how much kinetic energy was lost in this collision. The initial kinetic energy, we do separately. We had a 1,000 kilogram car going 15 meters per second, and we have the kinetic energy from our 2,000 kilogram truck that's only going 10 meters per second. And we get this combined 212,500 joules. I won't worry about significant digits for initial. The final, now we have a mass of 3,000, and we have a speed that was like 8.33. I'll put a few extra threes if we need to. That came out to be approximately 103,333, I think. When we subtract, we get 109,167 joules, or about 1.1 times 10 to the 5th joules lost. Where did all the energy go? It got turned into heat. It went into crumpling up those car hoods. It went into lots of stuff, but it's no longer kinetic energy. Okay. Inelastic collisions are actually really pretty easy. Elastic collisions can seem a little harder. Let's look at an example there. In an elastic collision, momentum and kinetic energy are conserved. Well, momentum being conserved, let's limit our system to two things, A and B. It's going to look like this. Relative momentum being conserved looks like this. Mass A, velocity A initial, mass B, velocity B initial, has to equal mass A, velocity A final. A plus mass B, velocity B final. That's one equation. Okay, assuming that we know the initial conditions, mass A, mass B, velocity A initial, velocity B initial, the masses don't change. But notice we have two things here, final for A, final for B. We need another equation if we have two unknowns. And our other equation, of course, is conservation of kinetic energy, which is going to look like this. 1/2 mass A, VAI squared, 1/2 mass B, VBI squared, equals 1/2 mass A, VA final squared, plus 1/2 mass B, VB final squared. Whew. Two equations, two unknowns. This one's linear looking. This one's got a lot of squared velocities. It looks kind of quadratic. It's not an easy system. If you want to follow through the book, they will help you combine those. But the bottom line is, the book puts them together. That gives us a second equation that's much easier. VB final minus VA final. In other words, the relative velocity from B to A is equal to the opposite of VBI minus VAI. The relative velocity after the collision is the opposite of the relative velocity before the collision. This is a much easier equation to use. So now we have this equation and this equation. We have two linear equations. What this means is that before the collision, object B is going 5 meters per second faster than object A. After the collision, object B is going to be going 5 meters slower than object A. Make sense? If you want to think about it, there's a directional thing in there too. But the relative velocity, so this is kind of an important idea, and it's going to make it easier to solve. So I'm going to get rid of this one, because I think that one's not as helpful. But you can see they used that one with this one to get this. Okay, so there's my two equations. Our problem involves our gliders on an air track again. Same two gliders. Let's look at this as an elastic collision on the air track. And here's what they tell us. Here are the initial conditions. Mass A is 0.50 kilograms, and its velocity is positive 2, just like we had before. Mass B is 0.30 kilograms, and its initial velocity is negative 2.0 meters per second. If we know our initial conditions, and we've got two equations, we can solve for the final velocity of each one of these. We just have to use what they've given us. So let's use that first equation. Conservation 0.5 times 2 plus 0.3 times negative 2 equals 0.5 VA final plus 0.3 VB final. All of that can actually combine and gives us something like 0.4 equals 0.5 VA final plus 0.3 VB final. So now we're kind of stuck, so we need to use our other equation. Our other equation says, look what you had before. B minus A, negative 2 minus 2 equals the opposite of VBI minus VAI. We're going to have to solve one of these and substitute it in, so I'm going to go ahead and solve this one. That gives me negative 4 equals the negative of this, or 4 equals VBI minus VAI, or let's substitute in for 1, let's decide VBI, I'm sorry, that's final. I botched that one. We're going to start over right here. I put those in the wrong place. VB final minus VA final is the negative of negative 2 minus 2. I still get the same number, but this looks better. VB final minus VA final equals 4. Or VB final equals VA final plus 4. I want to substitute that result right here. Right there. Well, let's go down a level. Right here. I took that second equation. I don't know finals, but I know initials. And that's what it gave me. So let's do that. I'm going to have to race to make room. So I've got 0.4 equals 0.5 VA final plus 0.3 times VA final plus 4. That's what we substituted in. It's down to an algebra problem now. We've got one unknown, so let's see if we can work it out from this point. 0.4, 0.5 VA final, plus 0.3 VA final, plus 4 times 0.3 is going to be 1.2. If I subtract 1.2 from both sides, I'm going to get 0.8 equals 0.8 VA final. So it looks like VA final equals 1.0. I have a sign error right here. This should be negative 0.4 minus 1.2 is negative 0.8. So VA final is negative 1.8. That makes sense. It hit, it bounced off going backwards. It came in going positive 2.0. When it bounced backwards, it's going negative 1.0. This part in blue that I left in blue, that's our VB. VB final is equal to VA final plus 4. Well, that's going to be negative 1.0 plus 4. So, VB final is a positive 3.0 meters per second. If we wanted to do a check on that, we could actually check and make sure that our kinetic energy before and after the collision is conserved. But I promise you, without doing it, that the kinetic energy before and after the collision was conserved. Okay, but one more idea in this chapter, and that's the idea of momentum and the impulse momentum theorem. If you want to change an object's momentum, let's think about it. How do you change something's motion? The only way to change something's motion is to exert a force on it. Okay? It also makes sense, though, that the longer you exert the force, the greater change that momentum will have. It's an underlying principle in most sports. If you play baseball, they tell you to follow through. And the reason they tell you to follow through is when the bat makes contact with the ball, if you just stop, your ball kind of goes bloop, bloop, bloop. It's like a bunt. If you want it to really go far, you want to apply that force for a long time. So you keep your bat in contact with the ball as long as possible. I call it following through. You do it in golf, you do it in tennis, you do it in soccer, you do it when you shoot free throws and basketballs. If there's a sport with a ball, the chances are that at certain times your coach is going to say, you need to follow through because they want you to maintain that force in contact with the ball longer. Brings us to the last section that we're doing. This chapter's got more sections, but we're only going through 8.5. 8.5 is about impulse. Impulse is a vector quantity. The impulse for symbol is a capital J. And it's equal to the force times the time interval. The impulse is in the direction of the force. So the greater impulse, you can make an impulse larger by using more force. And you can make an impulse larger by using more time, extending that. The unit is not a special unit. It's a Newton times a second. So there's our SI unit. It is a vector. You're multiplying newtons times seconds. It's a Newton second. Now, there is an interesting thing. Let's think about what a Newton is. Remember, we get newtons when we do mass times acceleration. That's how we defined forces earlier. The net force is mass times acceleration. A Newton is a kilogram meter per second squared. If we multiply that by seconds, we get kilogram times meters per second. This is what we normally use to measure impulse, but this is what we use to measure momentum. It reminds me very much of the relationship between work and energy. When we do work on something, we change its kinetic energy. When we apply an impulse to something, we change its momentum. In fact, that's what the impulse momentum theorem says. It says that the impulse, which we say is the same as F delta T, equals the change in momentum. But I'm going to rewrite that a different way. The impulse is equal to the change in momentum, which means impulse is this. Now, once again, most of the time, and in this class all of the time, the mass of the object will not change. We don't have quite the sophisticated calculus we would need to consider an impulse or situation where we had a time-varying mass. So we assume our mass is a constant, which means we get this relationship. But I really think it's important. Impulse is a change in momentum. You can accomplish the same amount of impulse with a really small force if you apply it over a long time as using maybe a really large force applied over a very short time. One of the principles on how things like airbags work is by increasing your stopping time. We go back to this definition. If I increase my stopping time, the force that's exerted on me is going to be much, much smaller. If you're in a car and you get in a car accident and you go from 50 miles an hour to 0, your change in momentum is the same. Whether you go from 50 to 0 like that, or whether you go to 50 to 0 more slowly. You can't change your change in your momentum. It's going to be your mass times your change in velocity. But you can change how much force is exerted on you. If you want to decrease the force, increase your stopping time. That's what airbags were designed to do. They make it, you take longer to stop. Same thing with safety nets for high tightrope walkers. They fall off the tightrope, they still end up going 0. But the difference is, how long did it take them to stop? Those sudden stops have really huge forces. You don't want a quick stop with a huge force. You want a slow stop with a much smaller force. Let's do one problem. Oh, one more thing while we're thinking about it. We're kind of acting like there's a constant force, but the truth of the matter is, most of the time, it's not really a constant force. We can use a constant force, but we can also use an average force. Like you might think that when you hit a baseball, that the force exerted on the baseball looks like this. You exerted it for whatever time that is, from t equals 0 to some other time. But the truth of the matter is, when it barely made contact, you weren't exerting that much force. It probably exerted a force that looks more like this. But the average force works just as well. So we use an average force when we don't have a constant force. All right, let's do an example. Suppose you throw a baseball against a brick wall. Here's a brick wall. Okay, you've got a baseball coming in. It's this looks more like a softball or something. It's bigger than a baseball. 0.40 kilogram. And it has this initial velocity, and I'm going to put negative 30 meters per second because the way we've drawn it, it's going to the left. It hits the wall and it bounces straight back, and it's got this final velocity of 20 meters per second. Notice it lost some kinetic energy. It's not going to have as much. That's pretty typical. You almost always, when something hits something and bounces off, we lose a little bit of that kinetic energy, but we don't lose any of our mass. So it says if it was in contact with the wall for 0.010 seconds, can we find the average force? We sure can. We know that the change in momentum is equal to the impact. If we want to write it down like this, there's the impact. It has to equal the change in momentum. Well, we start our, remember, anytime you do change, be sure you're doing final minus initial. So 0.40 times 20 minus 0.40 times negative 30. A lot of times people miss one of these signs. This is a big change in momentum because you went from a negative velocity to a positive. In fact, anytime something bounces off something, that's going to require a greater change in momentum than when something just hits it and stops. That makes sense. It's going to take more force, that wall has to exert more force to actually make the baseball go back the opposite direction than it would require to just make the baseball stop. All right, so let's go back to our math. We've got 0.01 F equals, that's going to be 8, that's going to be 12. This whole thing comes out to be, this side is 20 kilogram meters per second. So that's our change in momentum. If we divide it by 0.01, we see the force is going to be 2,000 newtons. These aren't difficult problems, but you do need to remember that both momentum and impulse and velocity, they're all vectors. Watch your signs. If this is a negative velocity, this is a positive velocity. Change in velocity, change in momentum, final minus initial. The big idea there is the impulse is the change in momentum. Generally, if something is moving and it comes to a stop, that's a set amount of change in momentum. You can't alter that, but you can alter how it happens. Do I want to use a big force for a short period of time? Do I want to use a small force for a long period of time? Okay, that finishes chapter 8. We're stopping with just 5 sections, so we kind of get a little reprieve here.